All right, so this one was, I believe, from 2015. Part A just wants you to sketch the slope field at the 6 different points that they give you. And so you really just want to plug in each point and figure out what you get when you plug in each of the points. So at x equals 0, y equals 1, looks like it should have been a slope of -1. 0, 2 should have been a slope of -2, so steeper. Maybe not quite that steep. Maybe like that. That looks better. 1, 1 should have given you 2 minus 1, or a +1. And then 1 for x and 2 for y should have been 0. And then 0, -1 should have been a +1. And 1, -1 should have been a slope of 3. So pretty steep there. And that was worth 2 points. So you literally got 1 point if you had this single one correct, because it's giving you 1 point for all the ones where the slope is 0. And you got 1 point for all of the rest of them. So 2 points for part A. Any questions there on part A?
Are they going to be super like nitpicky about like your slopes, since we don't have to show the numerical value? Are they going to like be super nitpicky about, oh, that doesn't look like 3, that looks like 2? Or are they just going to like give it to you if it's anything close?
If it's pretty close, you're fine. I mean, if it's 0, it should look like 0. If it's undefined, it should look vertical. And, you know, I mean, your slope of 1 shouldn't look like this or like this, you know. I mean, it's got to be pretty close to 1. But, you know, they're not gonna get out a ruler and measure your line to make sure that it rose exactly the same amount that it went to the right.
Okay.
Pretty close is good enough. All right, part B says find the second derivative of this in terms of x and y, and then determine the concavity of all solution curves in quadrant 2. So first off, to find the second derivative, this is part B. To find the second derivative, we'll just take the derivative with respect to x. So the derivative of 2x is 2, and the derivative of minus y is minus dy dx, which is 2 minus dy dx, 2x minus y. So we'd probably write that as 2 minus 2x plus y as our second derivative. And getting your second derivative was worth 1 point. And then your reasoning why all points in the second quadrant are positive. Well, in the second quadrant, quadrant 2, x is negative, y is positive, so you end up with a positive and another positive and another positive. Okay, so 3 positives certainly is greater than 0. 2 minus 2x plus y is always greater than 0. For x less than 0, y greater than 0. And just an explanation of that, basically, I mean, a basic enough explanation as to what I just did there is good enough. Good or no?
Do we need that sort of, not really algebraic proof, but that like algebraic kind of reasoning there? Or could we have like just reasoned it out like using words, or do we have to show that like 2 minus 2x plus y is always greater than 0 and then break it down that way?
I mean, if you just said x is always negative, y is always positive, and that makes the second derivative always positive, you should probably write so concave up. That's good enough.
Okay.
Everything I wrote. I mean, you need to write something about x is going to be negative and y is going to be positive, which makes the second derivative always positive. You didn't need to algebraically write it out. You write it out in words in some form, but something that makes it clear that that's always positive. All right. So part C, y equals f of x, is the particular solution to the differential equation with the initial condition that f of 2 is 3. And we want to know if f has a relative minimum, relative maximum, or neither at x equals 2. Okay. So in order to figure that out, it's got a minimum, a maximum, or a 0. We're looking for what does dy dx equal at x equals 2. And x equals 2 means y equals 3, because that's what was told to us right here. F of 2 is equal to 3. And so our derivative, which was 2x minus y, evaluated at 2, 3, just gives you 4 minus 3, or 1. And if my derivative equals 1, am I going to have a relative max or a relative min there?
No.
Nope, only if it's 0 or undefined. So we'll say neither max or min at x equals 2. And you got 1 point for trying to find a value here, looking at 2x minus y at 2, 3, and 1 point for the answer that no, there is not one. Good or no?
Good.
All right. Part D. Part D says find the value of the constants m and b for which y equals mx plus b is a solution to the differential equation. So I'm going to just write that. We want y equals mx plus b as a solution to dy dx equals, what was it? Dy dx equals 2, was it 2x minus y or 2y minus x? 2x minus y. Okay. All right, so this one is actually a little, it's not super complicated, but it just seems a little confusing. So we want the solution to our differential equation to be this nice linear little line here. Well, what do we know about the value of m? M is a slope, true? Should know that m is a slope. And the slope of the solution should be the derivative. So that should tell us that the value of m should be 2x minus y. Right? Because if I were to take the derivative of this, all I'm going to get is m. So m must be my derivative. So I could then go in and rewrite this. I could go in and rewrite my my derivative here as 2x minus my y value, which is mx plus b, is equal to dy dx. Well, dy dx is 2x minus y. Everybody agree with that?
How did you get m equals 2x minus y? What'd you do there?
Well, I mean, that's just what the slope, the derivative of this is m, and it's also 2x minus y. Right, I mean, the derivative, this is the solution to my differential equation. So the derivative of my solution to this should be this.
Okay.
But I should be able to take the derivative of y equals mx plus b. The derivative of y equals mx plus b, right, y prime here is m. So m must be 2x minus y. So we've got 2x minus mx minus b equals m. Do y'all agree with that?
Yeah.
Okay. So from there, what we're going to do is we're going to bring the m that's on our right-hand side over here back over to the left-hand side, and we're going to use this cool little trick. We're going to say 2x minus mx minus b minus m equals 0. And then I'm going to factor. What can I factor out of these first two terms?
X.
X out of them, right? So that gives me x times 2 minus m, and then minus b minus m equals 0. And so how many x's are on the left-hand side over here?
One.
Nope. How many x's do I have?
2 minus m.
I have 2 minus m x's. How many x's do I have on the right-hand side?
0.
Yeah, don't the number of x's on the left-hand side need to equal the number of x's on the right-hand side?
Why?
What?
Why would they need to equal? Didn't we just create an equation?
Yeah, I have an equation. Don't both sides of the equal sign need to be equivalent to each other?
Yeah.
Yeah, so if I have 17 x's over here, don't I need to have 17 x's over here? Otherwise, they're not going to be equivalent, are they?
Well, all that could simplify down to 0, and then it would be equal.
I mean, true if I knew the values of m and the values of b and the values of x, but I don't know all those things. Right? The number of x's on the left has to equal the number of x's on the right, which means that 2 minus m x's has to equal 0 x's. And that all of the constants on the left, negative b minus m, needs to also equal the constant on the right, which is 0. So both of these things need to be true, which tells me that m must be 2. And that would tell me that negative b minus 2 is 0, or b is negative 2. And that's, I mean, that's a trick, this little trick of setting these constants and the values of x equal to each other on both sides is something that normally is taught in pre-calculus when you learn how to do partial fraction decomposition. I don't know, those of you that took pre-calculus last year, I don't know if you ended up learning about partial fraction decomposition, but you should have. Let's take the number of x's on the left, set it equal to the number of x's on the right, and solve. Same with constants, equal to constants. So that's our answer. And they gave 3 points for this. Let's see. One for showing that the derivative here was m. That was 1 point. 1 point for this, and then 1 point for this at the end. Any questions on that one?
Nope.
All right. Let's see. I believe I asked you guys to do this one, yeah?
Yeah.
All right. How'd that one go? How'd the last one go? You get 9 out of 9?
Nope.
No, but probably everything up till that last point, maybe. Maybe. All right, well, let's take a look at this next one. So I believe this one was 2014. It asks us to sketch the solution curve through the point 0, 1. So there's my point 0, 1. Clearly goes up and curves back down. This goes down and curves back up. Looks something like that. The second half of that maybe didn't look so great. maybe more like that. I didn't quite have my little minimum there in the right place. But that's basically what that looks like. You get 1 point for that. Hopefully that part was easy enough. Should have all got the 1 point for A there.
Yeah.
All right, part B says write the equation for the line tangent to A at the point 0, 1. And so we're going to use the equation to approximate f of 0.2. So first thing we need, we've got a point, right? We're going to use 0, 1. Second thing we need is a slope. So that means we need to evaluate dy dx at the point 0, 1 to find the slope of that tangent line. So 3 minus 1 ought to be 2 times the cosine of 0, which is 1, gives us a slope of 2. So we should end up with y equals 2x plus 1. I mean, that's already a y-intercept, right? So we can just use slope-intercept form. 1 point for that. And then 1 point for properly approximating f of 0.2. That'd be y equals 2 times 0.2 plus 1, which is 1.4. And 1 point for that. Everybody good there with A and B?
Yep.
All right, and then part C just asks us to solve that differential equation using that particular solution, f of 0 equals 1. So I'm going to rewrite this over here, dy dx equals, I forgot what it was, 3 minus y times cosine x. Okay. So 1 point if you properly separate the variables. Two points for your antiderivatives if you get them correct. So the right-hand side should have been pretty straightforward. The right-hand side would have just been sine x. And we'll put our plus c there. And then this side, you would have had to do a simple u sub u equals 3 minus y. And d would be -1, so you'd end up putting a negative inside and a negative outside. So you'd end up with negative natural log absolute value of 3 minus y. And so 1 point for properly separating, 1 point for each integral, and 1 point for having the constant in this one. And then you needed to plug in your initial condition, which was 0, 1. So x is 0, y is 1, gives you negative natural log of 2 equals sine 0 plus your constant. So your constant is negative ln2. You got 1 point for properly using your initial condition to get your constant. And then you went back in, negative natural log absolute value 3 minus y equals sine x minus ln2. And you went through and tried to solve for y, and that's your last point on this one, was to get it all the way solved for y. So first off, we can divide by the negative. So we can make this natural log absolute value 3 minus y equals ln2 minus sine x. Then we exponentiate both sides to make it absolute value 3 minus y equals e to the ln2 times e to the negative sine x, which should just be 2 e to the negative sine x. Everybody good with that?
Yeah.
Okay, then we'll clear off the absolute value, which gives us a plus or minus here. And we'll have to determine then which one do we want. So how do we determine if we want the plus or the minus? We need to go back to our initial condition. If I plug in 0 for x and 1 for y, it needs to be true. So 3 minus 1 is 2, and 2e to the 0 is 2, but negative 2e to the 0 is not. So we're going to choose the positive 2e to the negative sine x. And so we have 3 minus y equals 2e to the negative sine x, using the initial condition to check that. And then we will subtract the 3, and then we will divide by the negative 1. So negative y equals negative 3 plus 2e to the negative sine x, and then y equals 3 minus 2e to the negative sine x. And that is your sixth and final part. Any questions on that?
I didn't initially divide the whole equation by -1, so mine looks a lot different.
Say that again, you divided it initially by -1?
No, I didn't divide it initially by, like, I didn't take the negative out of it, so I went through and exponentiated with negatives.
Oh, with the negative in there.
Yeah. And then I just like did 1 over those values to make them positive.
You did 1 over those values. So you did e to the negative ln 3 minus y. Is that right?
Yeah.
And so then you made that ln of 1 over absolute value 3 minus y.
Yeah.
And you did the same with this. You had e to the negative. No, you just had e to the sine x minus ln 2.
Yeah.
So you're negative 2e to the sine x.
Mm-hmm.
Yeah, that's fine. As long as you solve the rest of the way out correctly, that's fine.
All right, thank you.
Yep.
If you didn't if you didn't simplify the e to the ln2 minus sine x and just didn't make the ln2 into 2e, would you still get full credit?
Yeah, I believe so. I've looked through. I mean, it doesn't say that you need to simplify it. It's better if you do. All of their scoring guides always do simplify them. And like in looking through the student sample responses that they sometimes give, I haven't seen anywhere they've like said, you know, somebody put it and didn't simplify the e to the ln2 and still got points, but I've never seen it where, you know, somebody didn't simplify it, and you know, they always show, like, everybody always simplifies it in all the student samples that they give us. And so it's, I can't guarantee you that yes, you would get the points, but they usually state that things don't need to be simplified. So you're probably good. I would say 95% chance you're good.
Right.
Sorry, that's not, yeah, I wish I had a better, more definitive answer there, but. Let's see. I asked you guys to do this one, I believe, yeah?
Yeah.
All right, so should be pretty straightforward. This one I think was pretty easy, yeah? Part A, you probably note that writing these tangent lines thing that shows up pretty often. So I'm gonna write the tangent line to the graph of f at 1, 0. So we know we need to evaluate dy dx at 1, 0, which should be e to the 0 times 3 minus 6, which should give us a slope of -3. And then we'll have y minus 0 equals -3 times x minus 1. That's good enough for your equation, and then approximating it at 1.2. minus 1 should give you negative 0.6. And that was, let's see, 1 point for slope, 1 point for the equation, 1 point for the value at 1.2. So 3 pretty straightforward points there, I think, for A.
Even though this one only has 2 parts, is it still 15 minutes for it, time wise?
I mean, yeah,
Okay,
I mean, the assumption is that you have 15 minutes on average. It's not like you get 15 minutes.
oh, it's not like they stop
each
you
one.
after each one or anything like that.
Yeah. Yeah, so I mean, if you
Oh,
can
I
get
see.
through this one in 5 minutes, then, you know, that gives you an extra 10 minutes on the other 3
Oh,
non-calculator free response questions. You get
so
an
you can
hour
like
for the
manage your time
4.
that way.
Yeah, you have 4 non-calculator free response, and you get an hour total for them. So, yeah, so if you can do the first 3 in 10 minutes, you got 30 minutes to finish the last one. But. Part B, then just, I think, what did it say? It just wants us to solve it, right? Yeah, so this one's, and you'll note that the further back in time we go, usually the shorter the differential equation free response questions are in general. So let's take a look at B. We're going to solve this differential equation. So dy dx is e to the y. What was it 3 minus 6x?
3x squared minus 6x.
Squared minus 6x squared. Okay. So now we need to, for the first point, separate the variables, and that's always the first point. So dy over e to the y equals 3x squared minus 6x. And then we will integrate both sides. And this is the point where a lot of people start screwing up this integral and start writing natural log absolute value e to the y. You can't do that unless you do a u substitution, and you don't want to do that with this one anyway. This should become an integral of e to the negative y dy. And then this will become x cubed minus 3x squared plus c. At which point you get 1 point for this, 1 point for this, and then you still need to integrate, 1 point for separating the variables. You still need to integrate this, which is a u substitution, right? Let u equal negative y, you're going to put a negative inside and a negative outside, and the negative dy will cancel out. So you'll get negative integral e to the u, or negative e to the u, which is negative y. That's an integral you should be able to do pretty easily. But don't say, it's in the denominator, natural log absolute value of it. That only works if you do the u substitution to just get a u down here, which you can't do with that one, right? Because if you tried to let u equal e to the y, du would be e to the y, and you don't have another e to the y. So that's the first 4 points, and I think those first 4 points are pretty easy to get overall. And then you need to solve for your constant. What was our initial condition? That x equals 1, y equals 0, is that right?
Yes.
Okay, so we got negative e to the 0 equals 1 minus 3 plus c. E to the 0 is 1, so that's negative 1 equals 1 minus, well, write that out. Negative 1 equals negative 2 plus c, and our constant is 1. And so getting your correct constant is a 5th point. And then we've got negative e to the negative y equals x cubed minus 3x squared plus 1. And now you're just solving that for y. So first we'll divide by the negative. Then we'll take the natural log of both sides. Don't put this in absolute value because that's not what it is. That's only when you do your integration. And then take the opposite of it. y equals the opposite of the natural log of negative x cubed plus 3x squared minus 1. And that's one more point.
And you said we don't have to like write the restriction at the end.
That is correct. They always make a note of it in some way or another. I mean, you know, we could say, I mean, we're not going to be able to solve this one most likely. I don't know. I'm not sure offhand if negative x cubed plus 2x squared minus 1 factors. I don't know. I'd have to think about it for a minute, but you could just say negative x cubed plus 3x squared minus 1 has to be greater than 0 if you wanted to think about it. And that'd be fine, but you don't have to.
Okay.
Any other questions on that one? All right, I think I did not ask you to do this one. Is that correct?
Yeah, we haven't done that yet.
Did I ask you to do this one? Or this was the last one I asked you guys to do, huh?
Yeah.
Okay, cool. So how are we feeling about these just sort of normal differential equation ones with slope fields and solving with a particular solution and all that? Doing okay with them in general?
Yeah.
All right, cool. So then
Yeah.
what we're going to do, there's another type of differential equation question. And we're going to go way back up here to, let's see, that's not this one, about boiling a potato. And so I'm going to give you guys 15 minutes to read through this one and give this one a shot. We'll talk about this one, then I'll have you work on a couple similar to this tonight for your homework, and then we'll go through those other couple tomorrow in addition to the multiple choice. But we will, we'll have time to do this one and go through this one today before class is over. So I'm going to put on a 15-minute timer for you here, and we'll check back in then and work through it together we'll work through it together either way. So ready, go. So for part A with the potato problem, we're going to write the equation for the tangent line at t equals 0. For an equation for a tangent line, as we always need, what do we need? We need a slope and we need a point. Well, our point is given to us. They tell us that the point we're going to use is t equals 0, h equals 91. So we've got our point 0, 91. But we don't have a slope. And so we got to go back in and say, well, at t equals 0, what is dh dt? So we'll go in and we'll say dh dt evaluated at 0, 91 equals, and that's just negative 1/4 of h minus 27. There's no t involved in it, right? It's just negative 1/4 of 91 minus 27. And 91 minus 27 divided by 4 should give us 16. And so this is negative 16 for our slope. And so our equation should then end up being, did I say, right equation? Just write an equation. So we'll just say y equals negative 16t plus 91. So 1 point if you got the slope, 1 point if you got the equation. Everybody good so far with the equation?
Yeah.
Do
Okay.
they care if you use X or T?
Their guidelines use T. You should probably use T because that's what the variable is in here. So try to keep it to the same variables.
Do we have to use h then? Like h equals negative 16t plus 91? And is y like fine there?
Y, you should not use H because H represents this other function. H of t is this other function, right? This this is h of t, we could call that, you know, that's in its function notation. So when we write the equation of the tangent line, we write it as, you know, y equals whatever. Like normally with these other ones, let's see here. So like, right, we let y equals f of x is our particular solution, and we write it as our tangent line as y equals, and not like f of x equals. So if you wrote it as h equals, that's probably fine, but preferable to use y, but also use t. Okay, so then they asked us to evaluate that at t equals 3. Is that what it was? T equals 3. So y equals negative 16 times 3 plus 91. And that should come out to be, what is that, negative 48. That should be 43 degrees Celsius. And that's one more point. Hold on 1 second. All right, sorry about that. Apparently my dog is bleeding all over the place outside again. Should have been doing this a lot recently. Fun times. We'll deal with that later. All right, part B. Any questions on part A there?
Nope.
Okay. Part B, we're going to find the second derivative. So we're going to find the second derivative. They didn't give us a second derivative. So we're going to find the second derivative and determine whether our answer in part A is under or an overestimate. So our second derivative should be the derivative with respect to t of our original differential equation, which was negative 1/4 times h minus 27. Okay, and so the derivative of this should be negative 1/4 times the derivative of h with respect to t, which is just dh dt, and then the derivative of the minus 27 is 0. And so this should become negative 1/4 of dh dt. Well, dh dt was negative 1/4 of h minus 27. So our second derivative should be 1/16 of h minus 27. And so what does that tell us? It tells us that since, according to the original problem, h is always greater than 27, what can you tell us about the second derivative? It is also always positive, which tells us that the function for h is always concave up. And if we have a function that is always concave up and is positive, how will a tangent line approximate the value of the function nearby? It will always be less than the true value of h. And so our tangent line should be an underestimate. Does that make sense?
Could you just like plug in points to figure that out, or did you have to use like applications of the derivative to figure that
No,
out?
you need to use an application of the derivative. You need to state that the function is concave up. And therefore, since the function is concave up, it must be an underestimate. Any other questions there on part B? That was all of that was worth 1 point. All right. Part C then says for T less than 10, they're giving an alternate model for the internal temperature. some function g that satisfies this other differential equation. We still have the same initial condition. Now it's g of 0 equals 91. And we want to find an expression for g of t. So this time we need to actually solve this differential equation. So we're going to solve dg dt equals negative g minus 7 to the 2/3 power. So what's the first step on this going to be? We need to separate the variables, right?
Yeah.
It's minus
minus
27,
27.
not minus 7.
Minus 27. I guess, didn't I say 27? All right. Anyway, since this is dg dt and there's no t's over here, there's only g's, we're not really going to be just anti-differentiating both sides. We have to separate the variables. So this becomes dg over g minus, I almost wrote g minus 7 again, g minus 27 to the 2/3 equals negative 1 dt. Okay. And then we'll integrate g minus 7 to the 2/3 in the denominator. We'll integrate both sides here. And integrating g minus 27 to the negative 2/3. That should go up to g minus 27 to the 1/3. And then we got to divide by 1/3, so we're going to multiply by 3. And then this side should become negative t plus a constant. And let's see here. So 1 point if you separate the variables correctly. And then 1 point for getting the antiderivatives correct. And then 1 point if you got the constant of integration, but also went through and plugged in your initial condition. So our initial condition was g of 0. So when t is 0, g was 91. And what's 91 minus 27? That ought to be 64. Right? Cube root of 64 is 4, so we got 12 equals our constant. Everybody good there so far?
Yep.
Okay, so we've now got, and that's a fourth point. And so we've now got 3 times g minus 27 to the 1/3 equals 12 minus t. And we'll divide everything by 3. We will cube everything. And we will add 27. So we end up with g of t is equal to 27 plus 12 minus t over 3 cubed. And then I think they asked us, and so I believe that was one more point. Actually, that was not one more point. You had to get this and the value for g of 3 correct to get the last point. So we needed to find g of 3. G of 3 would be 27 plus 9 over 3, which is 3 cubed, should give us 54 degrees Celsius. And so both this and that together was your 5th point from C. Any questions on that?
Where's the like the 3rd or the 4th point? Like, because there's only like 1, 2, 3, 4. Where's the 5th one, or am I missing it?
Oh, sorry. No, I misread there. I just misread their scoring deadline. Sorry, 1 point for this and 1 point for this. Equation involving P and equation. Yeah. I think actually if you just had It's always confusing on these how they say. So like they say 1 point is for separating the variables. They say 1 point for antiderivatives. Then they say 1 point for constant of integration and uses initial condition. So I guess that's there. And then they say 1 point for equation involving G and T. So like, I think even if you got to here and didn't fully solve for G correctly, that could have worked for a point. Then it says 1 point for G of T and G of 3. So I'm going to go with saying this was good enough for the 4th point, but then to get the 5th point, you had to have both G of T solved for and 54 degrees solved.
Okay, thanks.
I think that's what they mean, but it's sometimes it's hard to tell. So, all right. So this is the other type where they give you usually a differential equation that only involves one of the two variables. And it's, I mean, it's the variable that's in the numerator of your dg dt. And so those ones get a little bit more complicated sometimes. And oftentimes they have this part where you're taking a look at the second derivative, determining its concavity and looking at a graph of it maybe, or determining what's an under and over estimate. Those pop up pretty often. Any other questions on that one? The infamous potato problem.